Hi there, my name is David and I'm presenting this paper on behalf of my team. We are working on the development of a magnetically compatible actuator for robotic interventions. So we are with the Hong Kong Polytechnic University and this is for Robio 2021. Yes, so this work is part of what we call robotic systems for medical interventions. So in specifically for biopsy. So in this type of applications, we generally want to introduce a biopsy needle into some tissues. We have been working on breast biopsy for some time. And here I only want to highlight the different modalities that there exist for imaging these tissues. We have MRI, we have ultrasound, X-ray, and there's some others. We're focusing on MRI because of the good tissue contrast that it provides. As a roboticist, this is also an interesting side part that we can see these medical images as some form of perception for the robot. Can we talk about MRI servoing? This is one of the concepts we like. So for this work, yes, so we have been motivated in developing technologies, robotic technologies to tackle to perform operations of biopsy for breast tissue. We know that breast cancer is actually one of the most common cancer amongst women in the world. So we really have a high rates. What a biopsy is basically doing is we may have some, well, in this case it's cancer, there might be some area of suspected, lump or hard region in the tissues. And the way we can determine whether it's a cancerous tissue or not is by introducing a small biopsy needle, and we will remove a small part of this tissue and then analyze it in the lab. So this is, demonstrating how it is done in the common practice with under the guidance of MRI. So the patient lays in a prone position, the breast is secure with a special type of grid, and the practitioner has to literally manually introduce the needle. So there are many problems. Whenever you have a person doing manual operations, if you compare it with a mechanical robot, of course, it will have not as precise or dexterous as a robot. So this is precisely what we want to contribute, is by developing some mechanisms that can help driving this needle into some areas of breast tissues. So we have many available options for driving the mechanism. So our focus in this paper is precisely on actuators. So we have all the standard classical approaches. We can use piezoelectric, we can use pneumatic, hydraulic, or even distantly moving or driving some tools inside the magnetic ball. So all of these have different advantages and disadvantages. We are following in this paper pneumatics because it's what we can call it clean, it's magnetically compatible, and it's relatively easy to control. So this is a project we had a couple of years ago. All this work has been mostly developed by he's a now gone research assistant that I used to have here in PolyU. And our objective was precisely to do this, to develop an entirely pneumatically driven mechanism that could drive this biopsy needle within or inside the tissues. So we collaborated with a medical imaging company here in Hong Kong, and our initial design was to have this 3 degrees of freedom robot. 3 pneumatic motors driving the canonical X, Y, Z directions of this system. Now, in this paper, well, the question that we're trying to answer is this: can this Tesla turbine be used as an actuator can it produce usable motions for a robotic mechanism? Before, just some background, what this Tesla turbine comes from it was patented by Nikola Tesla in 1913. It was originally designed as a power generator, so it was not really the fluid in this case was not pneumatic, but it was hydraulic. So you have water flowing into this turbine, and out of that flow you could extract or generate electric power. We're actually using this design as an actuator. I mean, can we, by sending pressurized air into these chambers, generate torque that we can use for driving a robot? So the basic operation principle, this very much heavily relies on what we call fluid structure interactions. So in this design, we can send pressurized air in either of these two inputs for the turbine. We have here in red and blue. Therefore, the actuator is potentially can be used as a bidirectional motor. So in this motor we have several discs here, kind of denoted here in this design, and the pressurized air will generate some vortex inside this chamber, and the vortex and its interaction with the discs will generate some torque. So this is the very basic principle on how this turbine works. Our philosophy for designing this motor is we don't want to use electricity, at least not inside the magnetic ball. Why we don't want to use electricity? Because if you use the common type of electric motors, the images from the MRI will not be good. I mean, you will see just noise. So to read the position of these motors, we are, well, basically just sending light inside the MRI room, and by using very standard encoding principles, by counting the number of pulses, we can estimate the angular position of this motor. So yeah, as I mentioned, this is the goal. So suppose we have actually this is some of the tests we did. This is some MRI machine inside the room, and our goal is to have a truly electricity-free robot or system. So this is the MRI room, a schematic diagram of it, and as we can see, we are only sending inside either optical fiber, meaning we are just sending and receiving light, and we are sending pressurized air. There's no electrical signals being sent inside this magnetic ball. All of this is with the aim of improving magnetic compatibility. So we started with a general 3 degrees of freedom design, and we actually are going to do this test with a much simpler proof of concept 1 DOF system. So we have our one of these Tesla actuators here. And then we have this 1 degree of freedom mechanism with a magnetic, with a biopsy needle attached to it. So we did some experiments, some position control experiments, where we evaluate we have to actually calibrate the pressure with the generated angular speed from the motor. And we can see it's kind of linear, which is a good thing for using for control. We do present some hysteresis, which is a drawback of these systems, because we have a static friction between the mechanical parts. We did some closed loop position control experiments, and the precision we obtained was generally okay. I mean, for our application scenario. We also assess the force that this mechanism could exert. For that, we just simply attach a force torque sensor. And we did all of this is valid in static conditions. So we could see that by sending 3 bar pressure as input to this turbine, we could generate statically around 36 Newton, which is okay for this system. So you can easily penetrate tissues with that force. So we did MRI compatibility experiments. This is actually a low intensity scanner. It's a 0.2 T scanner. And what the purpose of this test was twofold. One is to control in closed loop by using MRI images how much you're introducing the needle inside this phantom tissue. That's on one hand, to do closed loop control experiments inside a magnetic ball. And on the other hand, we want to assess the compatibility. We can see here that these images are not distorted, and we don't have any significant artifacts on them. Now we conducted further experiments. This is a much stronger magnetic ball. It's a 1.5T scanner. And in this experiment, what we wanted to assess is again, a magnetic compatibility, MRI compatibility. We compare the performance of our Tesla turbine with a standard off-the-shelf piezoelectric motor, and we can see that it's just completely electricity free. It's entirely a 3D printed robot. Of course, it's going to have a better performance than a piezoelectric motor in this case. So we have some simple conceptual video that we did a couple of years ago. So we show here a proof of concept, a prototype of this motor. Well, here I actually can conclude answering the initial question of whether a Tesla turbine can be used as a MRI compatible actuator to generate robot motions. I can say, based on this study that we conducted, that yes, it is possible. We can drive and generate usable motions for robotic systems. However, as any system, you have some disadvantages. Disadvantages that I can point is hysteresis, as I mentioned, is quite significant in this system. Another one is that the generated torque is not so much. You really need to use high reduction ratio in your motor because it's not so strong in many ways. So I finish here the presentation, and I thank everyone. And you can visit our website. And thank you.